Okay, so moving on to displacement. Who has a good definition for displacement? Or who has a definition for displacement? Anybody? This is one that we should have heard of before. I'm not looking for the water displacement. Niall. Okay, so it is the movement of one place to another. We're going to be using that definition more for like distance. So it's not the total movement. Anybody have a different definition? That's probably what came up first. Anybody have another definition? Have you guys learned displacement in math? No? Okay. So displacement is the how far from the start an object is. So meaning, this morning you guys woke up from your bed. You got dressed, you got on the bus or got in your car and made it to school. Your displacement is from your bedroom to where you're sitting right now. Okay? But at the end of the day, if we talk about your displacement throughout the whole day, where do you end up at the very end of the day? Back in bed. So you were not displaced then. You started and ended at the same place, so your displacement would be 0. Do you guys see the difference? All right. So distance would be the distance all the way to the school plus you're walking around in the school and then all the way back home again. That would be the total distance, but your total displacement from the beginning of the day to the end of the day would be 0. All right, so if we're measuring also, if you're walking some blocks and you walk a block north and then a block east, your displacement would be a vector. So it's a straight line from your start straight to where you end. All right, so it's not the total distance of your like 2-block walking. It would be that triangle, that angle, like you guys learn, what is that called? ABC on the triangle when you do the right angle. I'm like totally blanking it right now. The hypotenuse on the triangle. Have you learned how to solve that? A squared plus B squared equals C squared now? Okay, so then never mind. Maybe that's high school. All right, so anyway, do you guys get what displacement is? So we're going to use the definition of how far from the start an object is. Do you guys know what a vector is? No, so writing vector quantity isn't really going to help. So a vector talks about the size and the direction. So it's not the total distance. Remember, it's a straight line from the start to the finish. All right, so for this one, did anybody find an equation for this? This is more of a verbal an explanation on how to do the equation rather than like a set formula like a lot of the other ones are. So basically what you're going to do is draw a line from the start to the finish, and then you're going to measure it so if I measured a line, what would that be? Is that distance, volume? Distance. So what do I measure distance in? Not feet. That's inches. Meters. So inches and feet, that is the American way we do it. We don't do it. We're not using those in science. All right, so all right, so you're going to draw a straight line from the start to the finish, and you're going to measure the distance. And like Brian just said, we measure that in meters. So our unit of measurement would be meters. All right, so who can think of an example? I just gave you guys one. What would be an example of displacement?
I think I did it wrong, but I felt like the air that moves over the wings of an airplane, like the air displacement. But
okay, so that isn't, yes, we're not going to use that in any of the any of the examples we're doing moving forward. So I'm not going to write that one down just to not confuse people. Yep.
So like when you move from one couch to another couch.
Okay. So moving from one couch to another couch. I cannot see what that says. Good. Anybody think of anything else? Yep. Okay, good. Teacher. To the other. So teacher moving from one side of the board to the other. Students at home, you guys can participate too. Hello. Hello. Hi. Yeah. I know. Well, we were told that they get to pick. Oh, okay. It was kind of like in the future, and he made a big deal of mine, mine like down here. So he made a big deal saying, so don't think it's gonna happen right away, but it's not gonna work out. Story is 6, and then environmental. Yeah, something being put back in 7th grade. The 7th grade class. Yeah. Yeah, it's fine. Yeah. I know.
Agree to disagree.
No, I think that's the same thing. And then for the math, that's it.
Yeah, it's just Logan.
I don't know.
No, it wants it. Let me replay.
All right, so I'm just going to add the one other example of waking up in bed and ending the day in bed. All right, so I like the teacher one. Let's do the teacher one for a picture. All right, so while I search this up, we are on distance. Use this one. This is a lot of writing. All right, who has a good definition for distance?
The length between one point and another.
Okay, the length between one point and another. That would be actually a better one for displacement, right? Because displacement has to do with where you start and end.
Okay.
Your displacement definitions would probably be a better one for distance. So what would distance be? Or what? Yeah, Ryan.
I said the amount of space between two or more objects.
That would be another displacement one. Maddie? Okay, so it's the total how far someone or something has traveled. So total amount traveled. All right, good. So again, this isn't going to be a set formula because maybe I only take one step forward. So I only have one step would be about 3 feet. Or maybe I have the example of me going all the way from my bed to school, walking around the school, and then back to my bed again. That distance would be a couple of miles, right? So you would just add all of the, I don't want to use distance again, but you guys know what distance is, so I can use it. All right, so you add all the distance traveled. So if we're talking about distance, what do we measure that in? Meters, yes. All right, what would be an example? What's an example of distance? Anybody? Guys at home, don't forget you can participate.
I said like the units of measurement. I don't actually. I put how far the school is from my house.
Okay. How far the school is from my house. Good. So the unit of measure would go in the second one, Ryan. Okay. Good. How about driving 35 miles to complete all errands?
Yeah, really.
Are you guys okay with the difference between displacement and distance? Yeah. Nobody has any questions? All right, so we're going to use Brian's picture for his example for a picture, driving to school. All right, excellent. Moving on to time. What is the definition of time? Brian? Good, that's what I have. Anybody have something else? So she has a measured period during which an action, process, or condition exists or continues. Anybody find anything else? Beverly? Continued what? Existing as a whole? Okay, so continued progress existing as a whole. Good. Time is a hard one to describe or explain, but I think you guys would be able to define it or match it up with a definition. So the measurement of a period during which an action, process, or condition exists. All right, so again, I already told you guys there's no formula for this one. We could use like our stopwatch or whatever to measure the time. But what do we measure time in? Seconds, right. So you just need to write seconds for that second block, second box. All right, what are some examples? When will we use time?
Like when you do the 40-yard dash.
40-yard dash?
Yeah, I have that too.
You have that too? Okay. Good. When else will we need time? Eating food? Cooking food? Oh, yeah, okay. Maddie? I didn't even think about cooking, but yeah, we definitely need to know time. Not focus, right? Need to know time for cooking. All right, good. Let's do cookies. All right, slope. Hopefully you guys are familiar with slope. We all learned slope in math, right? Yes, good. All right, so what is slope? We also did slope when we did the paper airplanes. What is slope? Anybody? Guys at home, you can just call out. What do we find for slope, guys? Fabian?
Y goes down plus B. We'll put rise over run.
That is the formula for slope, but the slope is not, it's just the n in that whole formula.
Yeah. So rise over run.
Rise over run, good. That's what I was going to put for the equation. Did somebody online have something to say? So if I'm graphing slope, what does the graph look like? Is it a bar graph, a line graph, a pie graph? Is it a line? Is it a bars? Circle? It's lines, right? So what the lines, are they going to be like, what do the lines tell us? Or what are we looking for to know what the slope would be? Marvin? Think, if you guys are riding a bicycle and you want to go super fast, what kind of a hill are you going to go to the top of? Steep or big? Really steep, right? So the steepness of the line is our slope. So the steepness or incline of a straight line on a graph. So for us, we're going to be talking about the graphing part. All right. And then Fabian said rise over run. That would be our formula to get it. And there's not really units of measure for this one. All right, what are some examples? When would we want to know slope? Or when do we graph something that would have slope in it? We just graphed it. When we were graphing the paper airplanes, what were we graphing for the paper airplanes? They're what?
Distance and speed.
Time.
Distance and time, which equals? Speed, right. So speed. Can anybody think of any other time we would graph a straight line that would be a slope? This one you may not have done. Have you guys graphed acceleration yet? No. So
yes,
constant.
Yes,
you have?
Yes. I have, yes.
So constant acceleration would be a slope. A changing acceleration would not give us a straight line. It would be a curved line. All right, so I'm just going to type in slope. Anybody have any questions on any of these words yet? Everybody at home is okay? All right, so our next one is velocity. Velocity we really kind of talked about already. What would be a definition for velocity? What are the two things involved when we talk about velocity?
Speed and direction.
Perfect. Speed and direction. All right, and we already talked about the formula for velocity. Does anybody have what the formula would be? It's the same thing as speed. So, and we just said what the speed equation would be. So what's speed equal to? How do we calculate speed, guys? What is it? Distance divided by time. Excellent. So velocity, the only thing different with speed versus velocity is that we also have in a given direction. All right. So we're going to use the same units of measure as speed, which would be what? How do we measure speed? Distances. What's distance measured in?
Meters.
Meters. And time is measured in seconds. So it's going to be meters per second. What are some examples of when we would want to use velocity over speed? When would velocity be important? When would I want to know the direction something is coming at the certain speed that it's coming in? So I can maybe prepare, especially where you guys live. We definitely want to know these things. What could really cause a lot of destruction if we aren't prepared for something that would be coming at a certain speed in a certain direction?
Oh. No.
What? A car. Okay, so a car driving down the street. What else?
Hurricane.
Yes. So a hurricane. If we know the direction the hurricane's traveling in, we know what state it's going to hit or what islands it's going to hit. A lot of people can save their lives because they prepare and pack up and leave their house that live on the shore. We don't get it that much, but how many, you guys are really young. You probably weren't even just born for Sandy, right?
No, I was like 3.
You were 3?
I remember.
What? Yeah, I remember.
But you remember it, really?
I do.
Okay, so I mean you're still really little, but do you guys remember? Was anybody really hit hard with Sandy?
Yeah. Oh yeah.
Yeah.
All of our power and stuff went out, and something happened with our gas. We had to drive, and we kept driving north, but all the hotels were closed, so we drove 3 hours.
Yeah, it was crazy. Actually, my grandmother passed away right at the same time, and she lives in Texas, so I wasn't here for it. But I kept hearing everybody the lines for the gas stations were ridiculous. But even just right along the coast, you guys are so close to the coast, the water came in so far. And it wasn't even a hurricane. So imagine us getting hit by a hurricane. That would be crazy. Yep.
My parents, they were trying to make food and they thought they couldn't because of Sandy, so they left. And then when they came back, all of our neighbors were still there, and they asked how. And they said that they used the gas, but my mom apparently thought that if you didn't have electricity, you can't use the gas.
Yeah.
So they left this.
That is a really good lesson. Yeah, so, but running water you wouldn't really have. So toilets and stuff. So I guess you do have to kind of think do you want to stay and not have a toilet? It was also really, really cold. Was that Sandy already rained? That it was really cold. It was snowing out right after too. So you could have put your food outside and it would have been okay. All right, hurricane. So anyway, Katrina, which was way before your time, but have you guys heard of Katrina, the hurricane Katrina? A lot of people actually died because they're oh, it's going to be okay. But because of human destruction of the land, Katrina hit where it was very a swamp land, but people wanted to build houses there, so they destroyed the swamp and put more dirt. So now instead of having all those trees and swamp and marsh stopping a hurricane, it went right from the water into the houses. And so many people lost their houses. They still can't go back. They never have really been able to recover down there, which really stinks. So years and years later, they still don't have their houses where they were. All right, good. Moving on, we are on acceleration. What is the definition of acceleration? It has something to do with speed and velocity. Fabian?
The increase in velocity over time.
Yes. So I'm going to use the word change. So it's the change of velocity over time. So it's not always an increase because acceleration could actually be a decrease as well. Acceleration is also changing direction. So let's actually add that in there. So this is something you guys probably would not have found in your definition, so make sure you add this. So increasing speed, decreasing speed, and changing direction. So what this means, increasing speed, that means I'm going faster, right? So my velocity is changing. Decreasing speed, I'm slowing down, my velocity is changing. Changing direction is the hardest one for people to get, that you're accelerating. If you're going the same speed but changing direction, and this all has to do with velocity, what's the second part of velocity? Speed and time. Speed and, I just highlighted it. Direction. So if our direction is changing, our velocity is changing over time. So that means we are accelerating, even though we are going the same speed. Does that make sense to everybody? Anybody have a question with that one? That's the hardest one for people to get because you're still going the same speed. All right, what is our equation for velocity? This one I'm actually just going to copy from, not velocity, acceleration. What did you guys find for acceleration? Anybody? Go ahead, Fabian.
Something, but I don't really know what it means.
What is it?
I put A equals V minus VO divided by T equals V over T. Right? When V is the final velocity, VO is the starting velocity, and T is the elapsed time.
Yes, leave that one there. That's a good one. Some of you found F equals MA, right? If you have F equals MA, we're going to delete that equation. We're going to put the one that Fabian has. Because F equals MA, F is force and M is mass. So we're not going to be able to calculate the force and the mass based on the velocity of something. So we want to find the equation that has to do with velocity. So this is it. I just want to have what everything equals. Do you guys know have you guys learned this one where you use a triangle to solve?
No. Oh, yes, we are.
You have?
I am.
All right, this is a good one. This has everything kind of explained in it. So I'm going to put this picture here, and then I'm going to explain it to you guys. Okay. All right, it's kind of hard to see. Can you guys see that? So a change in velocity. Did we talk about the triangle? Some of your equations came up with a triangle. Did we talk about what that triangle means? All right, so this triangle right here. Moving forward, after 8th grade, in high school, you guys are going to see this a lot in math and science classes. All right, so you need to understand that the triangle is a Greek letter. Anybody know what it is? I know we always, yep. Delta. And in math and science, does delta mean something? Do you know? Okay. So it means change. So anytime you see this triangle, it means a change in something. Okay? And you're going to see it a lot over and over. So it helps to recognize what it stands for. So acceleration is a change in velocity. So that's where what Fabian was saying, the VF and VI. VF is just your final velocity minus your initial velocity. So the F and the I just stand for final and initial. And then we have our T for time. Come on in, Trevor.
Oh, sure.
All right, so again, it's a change in time. So how much time has passed? All right, does that make sense? We're gonna practice this a little too in class. So does anybody have questions on the acceleration equation? So if if we are talking about acceleration for the units, what would our unit of measure be? So we know what velocity is. It's right above it. So what's our unit of measure for velocity? Right up here. How do we measure velocity, guys? In what units? Right above it.
Just meters per second.
Meters per second. But then that is all over time. So what do we measure time in?
Seconds.
So basically it's meters per second per second. So I want you guys to look up here on the board really quick. All right. Keep forgetting to erase it. So we have meters per second. That equals this. So we have 2 seconds on the bottom. In math, you guys should have learned how to do this. If we have two S's, they represent the same thing. How can I write that to like condense it? There's 2 seconds. So what do I do with it? It's the same number. Anybody? It's not 2s because we're not adding it, we're multiplying it. So what does that mean? I know you guys learned this. Give it a guess. What will we do? There's 2 of them. 2 is the key word. We're multiplying them. We're not dividing.
S squared.
Yes, thank you. So that is meters per second squared.
It was that simple.
That's simple. Meters per second. All right, to do the square, if you highlight the 2, go up to format, text, and you're going to do like Superman flies, so superscript would make the little 2 up for the exponent. What are some times we would use acceleration? You guys at home can call out too. Don't forget to participate. What are some times we would use acceleration? Anybody?
How do I put the square?
Highlight the 2. Go up to format. The top thing, it says text. And then you're going to go over to superscript. Yep.
I said like changing speed to soccer game.
Okay, changing speed in a soccer game. What other, Maddie? That is the same one I actually have. Going from a all right, so going on to a highway, going from a stop sign and accelerating, going faster. Paying a toll. So on a highway, you have to stop to pay the toll. So you're changing how fast you're going. So slowing down is accelerating, and then speeding back up again is accelerating. So just to give you guys another example. All right, moving on to force. What is the definition of a force? Very simple definition of a force. Beverly? Okay, so the strength or energy of a physical action or movement, good. What would the action or movement be that would make the force happen? It would have to be 2 things. It could either be a blank or a blank. Anyone find that? Patty? Perfect. So a push. So I'm going to make your definition even easier, Beverly. So a push or pull. All right, what equation did we find for this one?
F equals mxa.
F equals, we're just doing MA. I don't know what the X, oh, the X is just times.
Okay. Oh, yeah.
So I'm going to just put the two letters together so we don't get confused. Okay. All right, where F equals force. Now, I just want to point out, so this F is capital. We use this, it's important in science and in math that you use the letters the right way with like either capital or lowercase, because capitals sometimes represent different things than the lower cases. Niall? Yeah. So force is capital F. M is the mass. And this is a little tricky because M can stand for other things also. One of your new vocab words that we're getting to is momentum. That M is a capital M. So that's how we're going to distinguish the difference between the mass and the momentum. We've also used M for meters. So it's a little tricky with that because we have to remember that M, when we're talking about like speed and velocity, that lowercase m is meters, and then this lowercase m is mass. And those are the only two that I think that lowercase m would ever represent. So you'll see that other letters get used where it doesn't really make sense sometimes. And it's because mass and meters are used often with lowercase m, so we have to use other letters to represent other words. And then we have A equals acceleration. All right, so what are some examples of when we experience a force or when we give a force? Pushing or pulling a what? Oh, okay, a door, good. Opening or closing a door. When else will we use a force? Okay, furniture across the room. Good. Any other times? Those are good examples. Marvin, can you think of any times we'd use a force?
Throw a ball.
Throwing a ball. That's funny. I was going to ask you to try to think of a sport one. And then so I'm going to do kicking a soccer ball just to give us another visualization for one more example of the force. But again, I'm not too worried about you guys understanding force. I think that's something that you guys should know already. 720. Anyone online have any questions? Are we all okay? All right. So the next three all deal with force. They will not have a set equation, not a set formula, but there is a way to calculate it. So it's going to be more of a description. So I did tell some of you just leave it blank. If you found something, I want to hear what you found. But I'm going to explain how to do it. So the first one we have is a balanced force. What do we have for balanced force? Definition. Maddie? So because it's balanced, what happens to the object? Does it move?
No.
No. Perfect. So when the forces do not cause the object to move. I'm gonna actually add, so when the total force is all right, so when the total force is acting on an object, do not cause it to move. Yep.
Let's say, like, for example, there's like a piece of wood on the floor and I'm standing on the wood, so pushing force against it, but the floor is also pushing force against it, and it wouldn't move. Would that be balanced force, even though the floor isn't pushing against it, it's just like really strong?
Yes, it is a balanced force. It would be like the same as you pushing against the wall. So the wall's pushing back on you, nothing's moving.
Would it still count as two forces? Or
yes.
One force?
You also have gravity. Well, I guess if you're standing on it, gravity would be acting on you. It would also be acting on the object as well.
But the floor would count as a force.
But the floor counts as a force also because it's going opposite. So that's one of Newton's laws of motion, which we'll get into. So for every action, there's an equal and opposite reaction. So the floor or the wall would just happen to be stronger, so it's not going to cause it to move. So yes, good question. All right, so for our, oh wait. Go back up to acceleration really quick. What do we measure acceleration in? Oh, sorry, force. What do we measure force in? Who got this one? What do we measure force in? It's a guy's name. I just mentioned him. Newton, perfect. Anytime there is a unit of measure that is named after a person, you always capitalize it. So Newton's is always going to be capitalized. All right, so now, kind of like what Fabian was saying, he's exerting a force on a piece of wood. The floor is exerting a piece of force on the piece of wood. If he's standing on it, the floor is pushing up, and then I go and push a little bit from the side, and it still doesn't move, I'm also exerting a force on the side. So there could be multiple forces acting on one object, right? So that's why there's not really a formula, because it all depends on how many forces there are. So basically, you would add up all the forces acting on an object, and they would equal 0 newtons. Does that make sense? So for balanced, it's not moving. So add all the forces and it would equal 0. Okay. So what would we measure a balanced force in? Newton. Perfect. So where is there a time? So we just said standing on a piece of wood. Yep.
Tug of war.
Tug of war. So before they start moving one direction or the other. So if we have an equal team and they start pulling and nothing happens right away, one team usually gets tired, and that's why the other team wins. But if they start right away and they have equal strength, they're not going to go anywhere. Good. Because Fabian just explained the standing. So standing on the piece of wood, I'm going to add that one in there too. Good. But let's do a picture of tug of war. Anybody have any questions on balance force? So if balance force, all the objects or all the forces acting on the object cause it not to move, what would unbalanced force be? What would happen? Right, so it would cause motion. Oops. Yes. Yeah. Okay, so our definition for unbalanced force would be forces that cause a change in motion. So we're going to use the same formula, the same way. We're going to add them all up, and it's going to equal greater than 0 or less than 0. depending on which direction it goes. So anything other than 0 would be an unbalanced force. And again, how do we measure forces? In newtons. All right, so what are some times we would add a force on something and it would cause it to move? Trevor?
Like a seesaw.
Okay. Seesaw, good. What else?
I said times where one side having was 5 people and one side having 1 person.
I'll say when one is winning. Good. What else, Maddie? Good. Anybody else? Right?
On a boat, when someone moves to the other side, it kind of tips.
Okay. Moving on a boat. I'm doing bad with my spelling today. All right. Is there one we don't have? Seesaw we don't have yet. Oh. I'm going to do a rocket. So that would be another good example of Newton's third law of motion. So rocket being blasting off would be an unbalanced force.
Miss Hudson,
Yep.
is there ever a time where there wouldn't be like a second force going against the first force? Like in any situation?
The only time, so like in outer space,
Is there not like air friction in space?
there's not. There's no air molecule. There's no molecules in space. So like if you threw a baseball in space, it will continue to go forever. On Earth, there's always another force. Because even if you throw a baseball going one way, you have all the air molecules pushing back on the other way. So you have friction, and then you also have gravity. So you always have gravity as a force, and then whatever other force you're adding to it. Good question. All right, so moving on to net force. Any questions right now with any of the forces? Are we all good? Excellent. What do we have as a definition for net force? Now, net force kind of describes a balanced force or an unbalanced force. It's kind of like the general term. Maddie? Perfect. So it's the sum of all the forces on the object. If it's balanced, then it would make it not move. If it's unbalanced, it would make it move. So net force is just adding all of the forces up. And you guys should be familiar with using the word net as like a total, hopefully. All right, so for our equation, again, it's more of a description. We're combining the forces. It's all addition. So we're just adding the forces together. And Brian, what do we measure it in? What did you guys put for examples for this one?
I put 2 elephants standing on a ball.
Okay. 2 elephants?
Yes.
You watching Dumbo?
No. Never seen it.
What?
Trevor?
Like a trash compactor with a wall closing out the trash?
Good. Anybody have any other ones?
That's the one where the elephant doesn't.
So I'm just going to add like pushing in an opposite direction.
What if you're like 2 people like carrying a couch going in one direction?
Okay, 2 people carrying a couch. I mean, really, it's anything that has to do with force. for this one, because we gave visual examples, for the picture example, I'm going to actually put up more of like an equation so you guys can visualize that. So again, you guys can add to.
Miss, that's a great over max print.
If you want to miss,
I'll watch it, yeah.
All right, so I'm going to use this. So when we calculate forces, this is what it looks like. So we use a box usually to represent the object, and then we draw a line to represent the force. The length of the line and the direction of the line tells us how strong the force is and in which way it goes. You don't have to worry so much about down here. It's just like adding all the forces up, but actually let's use this one because it's showing all different ways. So again, net force could be balanced or unbalanced. It's like just the general term, kind of like how speed is the general term for all the other speed ones that we did. All right, Brian, what'd you put for Newton?
Oh, I every time I researched it, it came up the guy.
The guy. Okay. Did anybody get a definition of like what for the measurement Newton, Brian?
A Newton is a force that will accelerate 1 kilogram of mass 1 meter per second squared.
1 kilogram of mass, 1 meter per second squared, right? So I'm going to add, so it's that, and then I'm just going to write how, it's on superscript. I'm just going to add how we measure force. All right, so I'm taking what Ryan just told us as far as the definition, and I'm writing that in a formula. So 1 Newton, oh, what did I just do? 1 Newton is equal to G is gravity meters per second squared. And of course we measure newtons in newtons, so I'm not going to add that because it's kind of repetitive. What did you guys get for any examples? Did anybody write an example for this one? All right, so that you guys can kind of visualize what 1 Newton would feel like. Holding a small apple or a lemon. That's what 1 Newton feels like. All right, so you can kind of sort of relate, like if you get a force of anything more or less, you kind of understand how much it is. Yep, Gianna? Go ahead. All right, so again, I'm just going to put a picture of
Just started last week.
all right, so again, for you guys to visualize it, I'm just putting a picture of somebody holding a small apple. All right, friction. That should be another vocab word you guys have heard about, but you may not. Do you do friction at all in 6th grade?
I think we did, yeah. I remember a little bit.
6th grade or 5th grade, maybe? Mm-hmm. What is the definition of friction?
It's like when an object is like rubbing against another object, so where it's like air encounters the other object, so it like slows it down because that one is still will go in the opposite direction, so it like pulls it with it.
Good. So opposite direction. So what would be applied in the opposite direction? A what? A force.
Would like rubbing your hands on like a rug or whatever?
Yes. So a force applied or a force going in the opposite direction of the motion. So yeah, rubbing your hands in a carpet, rubbing your hands together, running. You really feel the friction if you're running through water, running through the air. If it's windy especially, you'll feel it. But if you're going really fast, you'll feel the air molecules going in the opposite direction. Yep.
If there's wind going in the direction that you like throw a ball, for example, is there no air friction, or is there still like?
There's still always air friction, but the wind will actually carry it a little bit more. But there's still always molecules in front of, because the gas molecules move so fast, so there's still always molecules in front of it. But gravity would be what would really pull it down to the earth. But yeah, there is a little bit of air friction then still. All right, so on Earth, I also want you guys to add to this that on Earth, gravity is always a factor of friction. Anyone finds an equation for this? Anyone finds an equation if we're talking about force?
I just use like net force because you're taking away the negative force.
Okay, so we have net force. And I'm going to put the equation for force, which would be F equals ma. So what would we measure this one in? We're talking all about force. What do we measure force in? Newton. Brian's got the newtons down. Excellent. All right, so let's compare two things that might change friction. So in two different examples. So Brian, you said rubbing your hand on a piece of carpet, would that slow down your hand or would it make it go faster?
Make it go
slower, right, because you have more going against it. So when would a time be moving your hand against something make it go fast? When would it be like really fast to move your hand? Nobody? I mean, I guess you don't usually rub your hand on any surfaces. What about, let's compare sledding. When do you usually go sledding? In the winter when there's what? What surface are you sledding on? Snow, right? So the snow gets compact. When it's ice, you'll go really fast. When it's a fresh powder, you'll go a little slower. If I take my sled in my house somewhere and try to sled, what would be a surface that would make me go slower?
stairs.
Going down the stairs on a carpeted stairs, right? So that would make it go a little bit slower. Now, hopefully you guys don't do that.
Jeez, Scott. You guys got flip-flops, socks on.
Anybody have any other examples of friction, Maddie? Oh, a slip and slide, yes. And if there's no water, you jump and you get like rug burn all over your chest and it would hurt really bad. But if there is water, you're going to slide all the way to the end.
Oh, a balloon. When you rub it against the carpet and it gets all like shock.
That would... The friction does cause something to happen, but that wouldn't be... I mean, we wouldn't really feel the friction. We do that for something else. That would be for the static electricity. Okay, I like the slip and slide example. Let's make this our last one for today. Because it's really nice outside, so we can take a little bit longer math break. All right, so it's going to take us until Friday to finish. So on Friday, we're going to finish, and then you guys are going to start an escape room. All right, hopefully we'll have enough time to finish the escape room. The escape room is more just for you guys to practice. All right, does anybody have any